Okay, class, this afternoon we want to look at describing the direction cosines for a vector in a three-dimensional Cartesian coordinate system. So as we said before, in my Excel file, I've got a point at the origin, and then I've got another point out here at a location 4, 5, and 3 meters away. And I'm going to say that this is a force vector with a magnitude of 500 newtons. And what we want to do is define the direction cosines, which are just the projections of this vector magnitude on the x, y, and z coordinate axis. So what we're going to look for is, if this is the vector here from O out to point P, the shadow of this on the x-axis is this dark line here. So Px is just going to be this distance here. So let me call it delta x over the length of the vector L, which is the magnitude from O out to P. And then, well, this is going to be cosine of alpha, where alpha is the angle between the positive x-axis and the projection of this vector into the xy plane. And I'll define an angle beta. I'm going to say that the cosine of beta is simply delta y, or y2 minus y1 over the hypotenuse L. And then we'll have a third angle, gamma, that is the angle between the vector and the positive projection on the z, or the k-hat axis. So the cosine of gamma is going to be equal to z2 minus z1, or delta z over L, where L is just the total length of the vector. So we'll use the distance formula. That's going to be delta x squared plus delta y squared plus delta z squared, and we'd have to take the square root of that to get the distance. So let's go ahead and set this thing up. We know that point 1 is at the origin, so it has a location 0, 0, 0. Point 2 is at a location, what was it, 4, 5, and 3 meters away. So delta x is going to be x2, which is going to be 4 minus 0, and the distance length is meters. Delta y is going to be 5 minus 0 meters. And then delta z is going to be 3 minus 0 meters away. So I can figure out now the length of that vector by just saying that's delta x squared plus delta y squared plus delta z squared, and I have to take the square root of that to get the length. So L is going to be equal to 4 squared plus 5 squared plus 3 squared square root. Let me get my calculator out and see if we can do that. 4 squared plus 5 squared plus 3 squared. I get 50. So L is equal to the square root of 50, which means the length of that vector is going to be 7.0711 meters. And now what I'll do is go ahead and take my original definitions of the direction cosines and find alpha, beta, and gamma for this. And then I'll want a way to check to see if I'm right. So let's do that. The cosine of alpha we said was going to be delta x over L. So that's going to be 4 divided by 7.0711. So solving for alpha, I get this to be 0.5657, that ratio. And solving for alpha, I'll take the inverse cosine. I get that to be 55.55 degrees. So recall, that's the angle between the projection of F into the XY plane and the positive x-axis in the i-hat direction. So I get alpha is equal to 55.55 degrees. Now I want to move on and get the angle between the positive y-axis and the projection into the xy plane. So I'll say the cosine of beta is equal to delta y over L. So that's going to be 5 divided by 7.0711. And looking at that, I get this to be 0.7071. And now I'll solve for the angle beta by taking the inverse cosine. When I do that, I get exactly 45 degrees. So now I want to get the angle between the vector and the positive z-axis. So I'll call that gamma, the cosine of gamma. And guys, if you hadn't seen this, don't panic. We're going to use this quite extensively in statics and mechanics of materials and physics if you haven't seen it yet. So this is going to be delta z over the hypotenuse L. So this is going to be 3 divided by 7.0711. I get 0.4243. So gamma is the inverse cosine of that. And I get 64.9 degrees. Now, a way to check this to see if you got everything right is there's a trigonometric identity that says the cosine of alpha squared plus the cosine of beta squared plus the cosine of gamma squared has to be equal to 1. So this is a way to check to see if you've got the right answer. So I've got 0.5653 squared plus 0.7071 squared plus 0.4243 squared. And let's see if that does equal 1. 0.5653 plus 0.7071 squared plus 0.4243 squared. And I do get this to be equal to 1. So we did do this correctly. All right, now what we want to do is find the Cartesian components of this force vector in the x, y, and z direction. So this is very simple. We're going to take the dot product. The force vector is equal to the magnitude of the force. And I'll show that by using the absolute value sign. And the dot product of that with the unit vector will give us the components of the force in the Cartesian coordinate directions. So the magnitude of this was 500 newtons, and this is just like multiplying a scalar by my unit vector. And the nice thing about this is I just use the cosine of alpha. So I got the cosine of alpha and the I hat plus the cosine of beta in the j hat plus the cosine of gamma in the k hat or z direction. This times this will give me my answer. So I've got 500 newtons times 0.5653 in the I hat plus 0.7071 in the j hat plus 0.4243 in the k hat direction. Now, if I do this correctly, I should get the x, y, and z components of this force vector. So let's see, 500 times 0.5653 gives me 282.65. And I'm going to encourage you to put the units. This is a vector force in newtons, and this is in the I hat or the x direction. So I get 500 times 0.7071. That gives me 353.55 newtons. And this is in the j hat or the y direction. And then the final vector and component is going to be 500 times 0.4243. That gives me 212.15 newtons in the k hat direction. So guys, this is my force vector in Cartesian coordinates, I hat, j hat, and k hat. So if we've done this correctly, if I take the x value squared plus the y value squared plus the z value squared and take the square root of that, I've got to recover the magnitude of 500 newtons. So that's a second way to check it, see if you got the answer correct. All right, guys, we're going to move on, and we're going to write a little script file in MATLAB to calculate these direction cosines based on the coordinates of the 2 points. So we'll take a break right now and move on to the MATLAB. Thank you. Deanna, can you hand me my pen? My pen, I dropped it on the floor. You have a flash drive? Huh? Huh? I took mine out the other day and I don't know what I did with them. So we got to find them.
Actually, I went to get it. So when I was my first, I had all the school photos on it. It wasn't a pocket of a card stop. And you gone through the line and get my purse. The first one I pulled out, not the one I was, I had to be through the line on the one that did work. Let me see what I can.
See if I can find this. Just record it. Get on one side.